I'm going to try to keep this short because I don't think she needs much introduction, but it is my great pleasure to introduce Professor Anna Gilbert. She is the Herman H. Goldstein Professor of Mathematics at the Department of Professor of Mathematics at the University of Michigan, joint appointment with ECE. She's one of the giants of her field. She's won a number of awards, and she's done really some of the pioneering work in algorithms for compressed sensing, functional analysis, harmonic analysis, signal processing. And today she's going to be talking to us about some of her recent work on sparse metric repair. So please join me in welcoming Professor Gilbert.
Thank you. Thank you. It is a real pleasure to be here. This is my first time coming to Microsoft Research, and it's just great to be here. So I thought that in discussing the geometry of deep learning, rather than focusing on algorithms per se, I should talk about the geometry of data and the input to all of these algorithms. And so I'm going to talk about three papers that are joint in various subsets with Lalit Jain, who moved from Michigan to University of Washington, so he's local, and Rishi Santaya, who is my student at the University of Michigan, and then this cast of characters whom I have actually never met in person. So they're a lot of fun to work with, and hopefully I'll get to meet them in person one day. Okay, so I'm going to talk about the geometry of data, and in particular, repairing your data so that they adhere to a proper metric, so that they are no longer distorted, and hopefully are a closer approximation to reality than something that looks like this. We're going to go from distorted geometry to hopefully corrected geometry. Okay, and at this point I'm going to make my standard joke about English and about mathematicians. Mathematicians always like to say fix x blah blah blah, and I'm going to use the word repair instead of fix. Okay. What?
Until Korea won.
Yeah, there we go. Okay, got it. So what is the motivation? So typically, in just about any kind of machine learning type algorithm, we're given data. And maybe it's a similarity matrix, but whatever it is, it's a set of distances, or we calculate a set of distances in some way. And these distances are supposed to be from a metric. They're supposed to adhere to a metric. And in particular, when your data are from a metric, then you can run downstream unsupervised machine learning algorithms quite successfully, like clustering. In more traditional computer science world, there are approximation algorithms which will give you better guarantees if your distances adhere to a metric, much better than if they don't. And then, of course, there are all kinds of applications in computer vision and in computational biology which get better when your data adhere to a metric. Okay, so that seems to beg the question, how do we ensure that the distances that we're given, or the similarity data that we're given, how do we ensure that it adheres to a metric? Seems like a reasonable question. Okay, so what do I mean by adhere to a metric? So this is a crash course in basic analysis. So I'm going to assume that my matrix D is my set of distances, my matrix of distances, and it is distances amongst n points. It is a symmetric matrix. The entries are non-negative, and the distance from any point to itself should be 0. And the distances should satisfy a triangle inequality, the triangle inequality. So this is the statement that the distances adhere to a triangle inequality. Okay, right, well, check. I passed undergraduate analysis.
Well, are you fine with 0 distances?
What?
Are you fine with 0 distances?
No. Yeah, okay, fine.
Okay.
Okay. Yeah, that's actually not such the problem. Okay, so I can rewrite this system of triangle inequalities as a large matrix times the vectorized form of my distance matrix, just vectorize it. And then saying that my distances adhere to a metric means that this matrix times the vectorized form of this matrix are entry-wise greater than or equal to 0. And then what does this matrix M look like? Each row of M corresponds to a triangle, IJK. And the triangle inequality matrix is structured. There are 3 non-zero entries in each row. 2 of them are 1s, and 1 of them is -1. Okay, so I want M times the vectorized form of D to be entry-wise greater than or equal to 0. Okay, and so formally, what do I mean by metric repair? I mean, given some corrupted metric D prime, i.e. some triangle inequality is broken, then I would like to find a perturbation that repairs, not that fixes, but that repairs the corrupted input. And in particular, I want M times the perturbed input to be entry-wise greater than or equal to 0. Okay, makes complete sense. Okay, all right, here D is the corruption, P is the repair. Sorry, D prime is the corruption, D is the correction, is a correct version, P is the repair. Okay, and there are many techniques for solving this problem, maybe somewhat disguised, but there are a number of traditional techniques. So sort of most obviously closely related is a paper by Brickell et al. From about 2007 that solves this problem by projecting the corrupt data onto the subspace of metrics, onto the cone of metrics, and that projection essentially minimizes the L2 norm, or the Frobenius distance, between your corrected data and then your corrupted input. Okay? And that is the perturbation, and they give various algorithms for doing this. More specifically, instead of just correcting or repairing to any old metric, one could ask to repair or project onto the cone of Euclidean distance matrices. Maybe you feel very strongly that your distances should be Euclidean. This is otherwise known as multidimensional scaling. And it has extensive applications and development in the psychometric literature, and this is essentially the mathematical statement of what it means to repair your data to a Euclidean distance matrix in sort of to repair, give me the closest in Frobenius norm, the closest repair. You could also go back and do a little revisionist history. There's a lovely paper from the late 90s by Berger et al. That gives a randomized algorithm for metric repair in R3. Even more revisionist history. You could view some of the rigidity theory that Cauchy was working on in the 1800s as a way of asking about missing Euclidean distances and whether or not polygons remain polygons when you shake them and move them around. So the problem with all of these methods is that they perturb most of the distances, even ones that are correct, so to speak. So we want a more optimistic approach, and we want to assume that most of the distances are correct, and that only a few of them are actually corrupted, and we would like to make as few changes, as few repairs as possible, maintaining the original correct, we hope, structure of the data. Okay, so, well, what does that mean? We would like to make as few changes as possible. So that means we should minimize the L0 pseudonorm of the perturbation P, subject to the perturbation corrects things. This seems like a natural setup. Okay, great. We have a math problem. Alas, it's non-convex. One might be tempted. So this makes sense. This is the sparsest metric repair. Okay. One might be tempted to replace that non-convex objective function with a convex one. Please do not be so tempted because it doesn't work very well, at least not in the naive way. So the naive convex relaxation doesn't give the sparsest solutions in general, and it's just kind of not really the right setup of the problem. You can fix it, so to speak. You can repair this algorithm and come up with at least something in practice that's more sophisticated than this naive L1 minimization. But it's kind of the wrong approach to the problem, I think. Okay, so it's the wrong approach to the problem for a bunch of reasons. You might be tempted to think that it's the wrong approach because convex optimization will lead to a lot of constraints, possibly something like n-cubed constraints that come from each triangle inequality. And this might be computationally expensive. We might want to have rigorous guarantees about our algorithm. More importantly, we might want to exploit the combinatorial nature of this problem. I mean, there's a graph here. There are triangles. I can count them. So a seemingly easier question is, given a data set and given a matrix of distances, can we even efficiently detect whether the input is even a metric? Could we find the broken triangles quickly, maybe as a subroutine? Alas, no, probably not. So n cubed is probably where we're stuck at for this problem. So Williams and Williams showed a lovely subcubic barrier. So the following weighted problems either all have truly subcubic algorithms or none of them do. Okay, look, second on the list is checking whether or not a matrix, whether or not a given matrix defines a metric. Okay, so I'm willing to punt on n-cubed algorithms. I'm not willing to punt on convex relaxation. In particular, I'm paying attention to the first problem in this list, and that is naturally a graph problem. The all pair naturally also a combinatorial problem. The all pair shortest path problem. So somehow, all pair shortest path is somehow related to whether or not a matrix defines a metric. So let me use that as inspiration for diving more deeply into this problem of metric repair. And so in particular, I probably can't do better than a cubic algorithm. Okay, fine. Let's go explore some combinatorics. Okay, so I'm going to break down my metric repair problem into a couple of different cases. Not every case seems like it should be equally problematic. Or said another way, given a broken triangle, it seems like there should be a lot of different ways I could repair it.
So what is the objective now? What are we trying to do?
I'm trying to motivate you. There are three different kinds of problems. Okay, so I have a broken triangle, 1, 2, and 7. It's broken. Okay, and I want to repair it in such a way that my repairs consist of decreases in the original distances. Decreases only. I cannot increase things. Okay, so I've bowed out 7 to make it look like that's the leg of the triangle you should change. And you should decrease it. So I should decrease it to 3. Okay, this makes sense? Okay. Then the next case is maybe I take the point of view or I take the constraint that it's leg 1 that is too short for 1, 2, and 7. And I'm going to constrain myself to perturbations that only increase the length of some leg of a broken triangle. So I increase 1 to 5, and then my triangle is repaired. Okay? And then I could do, then I'm going to observe that the solution that I get in this case is not at all related to the solution that I get in this case. And in particular, a sparse decrease-only metric repair solution might not give a sparse increase-only metric repair solution. You know, imagine more than one triangle. So I have lots of triangles around.
Isn't it the case that in both cases you have a unique solution that an iterative algorithm will converge to? If you just decrease,
so it is true in this case. I'm going to tell you exactly what it is in a second. In this case, no. Well, iterative, how long does it take for the thing to converge, you should ask me, is really the question. Okay, so in this case, I'm going to tell you everything. Okay, so I'm going to consider these two cases separately. And then, of course, there's the general situation where we don't place any restrictions on the perturbation. We can increase some, we can decrease others. Completely general. So I can change 1 and 7 to 4 and 5, for example. Okay. And I'm going to look only at the decrease-only metric repair problem for right now because I'm going to dispense with it fairly quickly. I'm going to dispense with it fairly quickly by telling you should run the Floyd-Warshall algorithm on the complete graph, and you're done. In particular, if you go look at the Floyd-Warshall algorithm, it says if this triangle is broken, then decrease the length of that edge, decrease it to the shortest path. Okay, so when Lalit and I were working on this, we spent embarrassingly too long thinking about this problem, and he came in one day and he said, Anna, you know, I was a CS major. I learned this in my undergraduate algorithms class. I said, oh, that's good. I'm glad you took it. And what's embarrassing is that Brickell et al. Didn't notice this either. So anyway, Floyd-Warshall all-pair shortest path algorithm is an n-cubed time algorithm for decrease-only metric repair. And if you set d hat to be the all-pair shortest path solution for the complete graph with edge weights given by d prime, then the perturbation is simply the difference between the two matrices, and it is the correct thing to do. Intuitively speaking, to fix a triangle, what you should do is you should decrease this distance that's too big to be the shortest path between these two vertices. And so actually, Brickell et al. Actually noticed that part of this problem was related to the solution that you would get from running the Floyd-Warshall algorithm. So what they noted was that your corrected or any solution to the decrease-only version was element-wise smaller than the solution that you got from Floyd-Warshall. And then what Lalit and I showed was that this perturbation is, in fact, actually the sparsest possible decrease-only metric repair solution. So it is the sparsest. And in particular, it is also the one that has minimal LP distance to the input. So for any norm P. So not only is it the sparsest, but it's also the closest in L1 norm.
Just to make sure that's not like Stratton P, that's just LP?
Yeah, just LP. Yeah.
Also for P equals 0 or for only?
Yeah, it's the sparsest possible.
Only decrease only.
Yeah.
Okay, sorry.
Right, for decrease only. Okay, so check. This problem is done. An undergraduate algorithm will solve this. We're good. Okay. That suggests that we should turn our attention to the increase-only case and the general case, and I have bad news for you there.
So in the last line is one inequality, so the argument is the other way or this way? Is it decrease only? Or honestly, when you decrease...
Okay, sorry, I can't check this in real time. I'm going to assume...
It looks correct.
good.
Input and you decrease it to D.
Yeah, okay, so right. These are entry-wise smaller than that, so I've decreased everything. Okay, good. Test of eyesight and brain. Okay, so I have erased from the board the decrease only problem. That's solved. Everything is great. Let's turn our attention to the increase only case. And what could possibly go wrong? What kinds of problems might we have? Well, the problem that we might have is that if we have a broken triangle, so ij is greater than ik plus jk, we can't figure out a priori, we can't figure out which leg it is of this triangle that we should increase, that we should make longer. So, either this one is the right one or this one is the right one. And whatever choice you make may have some detrimental impact on the triangles that you want to repair sort of later on downstream in the algorithm. Okay, so also if you do just sort of a simple thought experiment and try and solve this problem by minimizing the L1 norm of the perturbation, there are lots of possible solutions, but few of them are sparse. So in particular, I can do all kinds of changes to my triangles, and keep the total L1 norm equal to 4. Lots and lots of different x's. Okay, so convex optimization is not a good approach even for this particular problem. I want some kind of combinatorial approach, and it's a hard problem. Okay, so I'm now going to tell you about extensions and generalizations of this problem so that you can see some of the increase-only metric repair solutions. So you can see, these are the results that are available. It makes sense to talk about them in the context of a general graph rather than a complete graph. I'm then going to tell you about using these algorithms to repair manifolds, or at least repair the distances that you calculate on a data set which you assume or hypothesize lies on some low-dimensional manifold. So we want to correct the distances so that one can do good low-dimensional embedding. And then what Rishi and I are currently working on is a bunch of algorithms for different kinds of metric learning using these techniques. Okay, so the first generalization and extension that I'm going to talk about, which is the graph metric repair, and it's a setting for which it's a setting which is natural to discuss the increase-only case. Okay, so I'm going to generalize from the complete graph to a general graph, and from broken triangles to broken cycles. Okay, so the idea. Why would you want to do this? The idea is that you might want to impose some kind of relations amongst your data points, like this data point is not at all related to that data point, and so I should not care about, in fact, I should ignore the distance between these two data points. You might want to say, for example, this data point is in a different cluster from that data point. You might want to say, hey, all of these data points are somehow related to one another, and so I should have edges in some graph amongst all of these guys and not amongst all of these guys, except for maybe one or two. So this is a generalization of the complete graph where I have all of the distances amongst all of the pairs of points. And hopefully you can see somehow, morally speaking, this is a broken cycle because this edge is heavy. It's too long. Okay. All right, so formally speaking, what is the graph metric repair problem? So I'm given a weighted undirected graph G and some set of allowed perturbation values. So a subset of R that I'm going to use to adjust the weights on my graph. Okay, and I want to find the smallest set of edges such that by modifying the weight of each edge in that subset S by adding some value from omega. So it could be positive, it could be negative, it could be both. The new distances on the graph satisfy a metric. So all the cycles are not broken, they're not too heavy, they're not too light. So this problem is, we called it graph metric repair. It's related to matrix completion, to graph cutting problems, to metric nearness, which is the problem from the Brickell paper, and related to metric embeddings with outliers. But this is the formal statement of the problem that we're interested in. And using this machinery, we're able to come up with a number of results for the decrease-only case, and then to study more thoroughly the increase-only and the general cases. So, as we discussed on the complete graph, the decrease-only problem has a lovely polynomial time solution, a cubic time solution. This is also true in the graph. And then we have a result that says that if you permit even just one single number in one single positive number by which you might potentially increase the distances in your graph, then the problem becomes NP-complete. So it's a radical change from decrease-only to increase-only. So then for the increase-only case, we have some approximation-preserving reductions from these graph cut problems. We also have several different approximation algorithms. They come in a couple different flavors. They're both, the two that are in the paper are each parameterized by different measures of how far the input is from a metric. So it's the length of one of the algorithms is the length of the longest broken cycle, and I think the other one is the heaviest weight or lightest weight, I forget, of the broken cycle. We also have a number of heuristics. So Lala and I did a whole slew of experiments and came up with some heuristic algorithms. They work well in practice on the kinds of random graphs and random data sets that we created. We can also show, at least for one of them, that the worst case approximation guarantee is like O of n. So they're great in practice and terrible in theory. Anyway, the main result that I want to at least tell you a tad bit more in detail about is we have a fixed parameter tractable algorithm for the graph, for a graph when this is a sigma, when sigma is chordal. And for any fixed constant sigma, there is an FPT. So I'm just going to give you a few of the key ideas in this algorithm, or in showing that there is such an algorithm, and in showing you that there's a verifier for a potential solution to this problem. And it goes back to the shortest path again. So if the shortest path between two adjacent vertices in your graph is not the edge connecting them, then something is wrong with this edge. And in particular, it's the heavy edge of a broken cycle. Okay, so remember the picture of the cycle where all of the edges are 1, except 1 is 10, and it's bowed out tremendously. Okay, so that 10 is more than the sum of these little lengths here, so something is wrong with that particular edge. Okay, and so there's a structural theorem that says, again, I'm going to tell you this is all for the increase-only case. For any positively weighted graph and a subset of edges E, a subset of edges S. S is a set of edges that is what we call a regular cover, i.e. it contains at least one edge from each broken cycle, if and only if F is the support to a solution to, this is the general increase, the general metric repair problem. Okay? And then, so that's one idea. It says, if you, right, it gives you a characterization of the solutions to the problem. Next, we have an algorithm that is a verifier. So suppose you have a potential set of edges S that might be a potential support for the solution. Then in n cubed time, you can determine whether or not there is a valid solution on that support S. And if it exists, then it finds it. And it is essentially reconfigure the weights in the graph that are not in, for edges that are in the potential set them equal to some large value. For edges that are not in that potential set, keep them the same, and then run shortest path algorithm in the new graph. And if the weights changed, then return how they were changed. Otherwise, it's false. Okay, so we have a result that says, we have a theorem that proves that this verifier does what it's supposed to do. And then we can use that to cook up an FPT algorithm, which I will not give you the full detail of, but I just want to tell you it exists, and this is the running time. Oops. Yeah, okay, sorry. That is correct. Whether or not this is practical, I don't know. How this compares to our heuristic approximation algorithms, I also don't know. This is what we can prove, and it's quite far from what we used. I can tell you this for the next setting. Okay, so I'm not going to go into details. It's kind of technical. Okay, so what I will talk about next is an application of these ideas to repairing your data that ostensibly you think lie on a low-dimensional manifold. Okay, so whether or not one believes this, I will leave up to you, but a typical model of real-world data is that it lies on a low-dimensional manifold embedded in a high-dimensional space, and there are all these fantastic dimension reduction algorithms that try to unroll, so to speak, or embed this manifold in low-dimensional space. I have a friend who's Swiss, and she tells me that there is no such thing as a Swiss roll in Switzerland. She says it's called something else. Okay, so how do these dimension reductions, how do they actually work? So what are their various building blocks? Well, first of all, they begin with some data, and then they compute a distance matrix, or perhaps you're given a similarity matrix, a distance matrix, and then you build a graph on those data points using your distance matrix as the edge weights of the graph. Maybe you adjust this a little bit. It's the geodesics. Okay, whatever, fine. They're distances. And then you look at maybe the k neighborhood of any given point, or you build a graph looking at just epsilon neighborhood of any point. You connect data points with edges if all those data points lie within some epsilon neighborhood of this other point. Whatever you do, you're building a graph, and you're using distance information to build this graph. And then the algorithms like these manifold learning algorithms like ISOMAP or LLE, they take this information to generate a low-dimensional representation of the data. And that's all fine and good. But what happens if you have a problem right here? Or a problem right here? So many of these dimension reduction algorithms have theoretical guarantees along the lines of if you add some noise to your data, and some noise, how much and what it looks like compared to the manifold, then the dimension reduction algorithm works relatively well. But I'm not a big fan of additive white Gaussian noise as a model for how my data get corrupted. In particular, many actual data sets have missing entries. You can't get, if you have survey responses, you can't get people to answer surveys. If you are looking at rating systems, you can't get people to rate every possible thing you might be interested in. If you ask people to rank various items, it's much easier to ask them to rank 2 items at a time as opposed to all n of them. I work a lot with computational biologists, and I work on single-cell RNA sequencing data, and many of those data sets have entries. They generate matrices where we do not know if the zeros are actually missing or if they're truly 0. And so once we have data that has missing entries in it, which is not at all a kind of additive noise model, then we can't accurately compute the distances or the dissimilarity matrix. So how can we possibly run these algorithms when the distance matrix is incorrect? It's even corrupted. So in particular, you might be asking, well, like how bad are these algorithms in the presence of corrupted data? The theoretical results hold. Okay, so I'm going to take the Swiss roll, and I'm going to compute the distances correctly. This is the original data set. I compute all the distances correctly, accurately, and I run ISOMAP, and I do the embedding. I unroll the Swiss roll, and this is what it looks like. Okay, so this is ground truth. And now I'm going to take my Swiss roll data set, and I'm going to corrupt it by computing first the distance matrix correctly, and then I'm going to decrease some of the distances. I'm going to set to 0 some of the distances. How exactly I do this, we can discuss offline, but I corrupt the distance matrix by decreasing some of the values and by setting some of them to 0. And I think I corrupt it by, it basically like saying I've corrupted 40% of the data. And then I run ISOMAP on the corrupted distance matrix, and this is the embedding I get, which looks like utter garbage. I mean, it doesn't even look like an embedding, like I'm missing points even. So ISOMAP fails completely when I have a corrupted distance matrix, one that is corrupted in this fashion. And a little foreshadowing advertisement for our algorithm. If we take the corrupted distance matrix and we repair it, as I'm going to describe in in a second. We repair it, and then we run isomap. The embedding or the unrolling, it's not as good as the true unrolling or the unrolling that resulted from the true distance matrix, but it's not bad. Okay, so this is an advertisement for the rest of this work. Right, there have been a number of different attempts, algorithms, to repair manifolds, to fill in missing data in manifolds. One of them is called nonlinear principal component analysis, and runs some autoencoder to come up with fill in the missing data. There's also something which now I have forgotten what mDRUR stands for, but basically you try and learn these mappings F and F. So in the presence of holes in your data set, you try and learn these two mappings, and so you iterate back and forth. And now I've forgotten what this acronym stands for. So these are the, in our paper, these are a couple of the benchmarks that we use to compare against. Okay, so now I'm going to state formally to you what I mean by manifold repair, and in particular, I'm going to state formally to you the types of corruptions. The types of corruptions that we're going to try and address. Okay, so we're given a data matrix, and we're given an oracle that tells us whether or not the ij entry of this data matrix is missing. And we wish to repair as sparsely as possible by making as few changes as possible the dissimilarity matrix that results from computing distances amongst points in X, so that standard dimensionality reduction algorithms like isomap produce good low-dimensional embeddings. Now, this is not the most formally precise stated problem. Good is in quotes. I haven't told you exactly how to compute this dissimilarity matrix. What do you mean by standard dimensionality reduction algorithms, etc.? So this is somewhat informal, and the results are actually going to be somewhat informal, but I think they're interesting.
So some entries are going to be missing in the corrupt dissimilarity metrics.
No, some of the entries are missing in the data.
So, but then
They actually, some of the entries could be missing in the distance matrix, but the assumption is that the entries are. I guess I should say some of the entries in the distance matrix could be 0. It's not that they're missing.
Oh, because you treat when you calculate distance between two nulls, then you
Yep.
just get no distance.
Yeah, you're jumping ahead. Yes, I got to explain to you when you have nulls in the data matrix, how do you compute the distance? All right, so you have to do something that's intelligent, which is why you need an oracle to know which one should I treat differently. Okay, so I will say that in the case of a bunch of applications, you may or may not know this matrix Q. You may or may not know which entries are missing or which entries are simply 0. So this is somewhat of a drawback for applicability of this work, but be that as it may. Okay, so Nati's question is, when you have nulls in the data, how do you, what does it mean to compute the distances between data points? And so what we're going to do is project the data points onto coordinates that are present in both in order to calculate the distance between them. So here I have the rows of this matrix are the data points, and wherever I have a star, I simply, in either data, in either data point, I simply ignore that entry in calculating the distance. Okay, so I've done a small example for the L1 distance amongst these 3 points, and L1 because it's easier to typeset without square roots. I end up with a distance matrix of this form. So it's not that I have zeros necessarily or missing entries in the distance matrix. I have missing entries in the data, but the distances do not adhere to a triangle, do not adhere to a metric. They don't obey, some of them do not obey the triangle inequality. This particular triangle is broken. 4 is bigger than 3. Okay, so what we should note about this distance matrix is that no distance is going to be too big because we haven't used potentially all of the coordinates to calculate the distances between points. So in particular, whenever we have a null, we just simply ignore it. So whatever distances are in there are too small, most likely, because we've thrown away entries. And so the right kind of repair that one should do here is an increase-only repair.
So could you explain how the bottom left matrix is produced from the top?
Okay, so we've got to do some arithmetic.
Yeah.
So, okay, so it's the L.
It's the algorithm, not the.
Oh, it's very easy. It's computing. I'm going to walk you through it. Okay, so I want to compute the distance between this point and this point. Okay, I'm too short to do this. That point and that point, okay? It's the L1 distance. Okay, so in this coordinate, I have both entries are present, so I have 1, because 2 minus 1 is 1. Okay, in this coordinate, they're both missing, so I ignore that. In this coordinate, the distance is 1, because 10 minus 9 is 1. Okay. So the L1 distance so far is 2. And then in this coordinate, one of these guys is missing, so I ignore it. That's the 2. Cool. So the algorithm makes sense? Yeah. Okay, good. And I have checked this arithmetic several times, so I think we're okay. And I even checked, oh yeah, this is really a broken triangle. 4 is bigger than 3. Okay, so we're going to repair this distance matrix by running a heuristic that we have, not any of our fancy theory, approximation, algorithms, FPT business. We just use a heuristic to increase these distances. Okay, now you can see what the right increase is for this particular example. Okay, so I'm going to tell you that there are some things that we can prove about this procedure in a very limited model case, and we can't prove a whole lot. So what we would like to show is that, first of all, there are 2 parts to the algorithm. One is in estimating the distances using this algorithm that Kostas and I just walked through. And then the second part is to analyze what impact our increase-only metric repair algorithm has on these data points, on the distances. So the first part is to say, look, if 2 points are far apart, then rarely should we bring them together. Should this distance estimation bring 2 points close together? Okay, and then if we are in the bad situation where we've brought 2 what should be far away points, if we brought them close together, then the increase-only metric repair algorithm or heuristic should separate them, should push them apart. Okay, so we can prove this statement in a model setting. We cannot prove anything that involves this part of the algorithm, and this is really only a model. So this is really simple. So suppose I have two Gaussian clouds that are mu1 minus mu2 apart. The centers of them are this far apart, and then they have got some variance. And I knock out each coordinate of these points that are in x and the points that are in y with probability 1 minus p. Okay, so each coordinate is present with probability p. Okay, so I've got 2 Gaussian clouds, and each coordinate of each point in these two clouds is present with probability p. Otherwise, I have nulls. Okay? Then this distance estimation step says the probability that any 2 points are this close together using this estimation procedure is upper bounded by this mess. For the sake of time and napping, I will not parse this carefully. One could parse it carefully later. Okay. In particular, one should say, what's the probability that any 2 points from these clouds are close together? How close are they? Are they within epsilon of n together, etc.? Anyway, okay. Okay, so that's it. That's all we can show is in this toy fake setting. We don't tend to, when we estimate distances, we don't tend to collapse 2 points when they shouldn't be. That's essentially what we say with high probability. Okay, so we can't say anything. We can't say anything good in theory about the heuristic that we used for the increase-only metric repair, other than it's fast. So there are a couple of different ways that we can ascertain how good these algorithms are for, or how good this particular algorithm is for repairing our manifold distances. So I'm completely giving up on any theoretical assessment. So that leaves me with 3 other assessment methods. The first one is eyeball, is create some synthetic manifolds and run isomap on them before and after knocking out data values and check what do the pictures look like. This is awful for a mathematician, but I just eyeball things. Okay, but it's not too bad, actually. So here are the embeddings under isomap for 4 different manifolds, which I have completely forgotten what they are like in higher dimensions, other than we have formulas. And so these are the projections or the embeddings that we get from isomap when we have the complete data. And then if we knock out 40% of the data values or the coordinates in these synthetic manifolds and then run isomap, and then correct the distances and then run isomap, it's not bad. It's not too bad.
So in the upper left, the first one kind of flipped, right, horizontally. How is that?
I have no idea.
All right.
I have no idea.
What was the question?
Why is it flipped?
No, it doesn't really apply to the other 3.
Oh, it's
only the first one, right?
It's just a random, right? I mean,
Isomap doesn't care about this.
Yeah. I don't know.
Isomap could keep you ready.
I hope I made clear that this is very far from a rigorous assessment of how good a job this does. The pictures look okay. To quibble about any details of them, they're pictures. What? It's not bad. It suggests we should do something more, right? The eyeball is just a terrible assessment. Okay, so how about I go look at a data set for which there are claims, whether you believe it or not, for which there are claims that a low-dimensional embedding is a nice way of being able to see clusters so you can classify better in this low-dimensional space. So in particular, take MNIST and run isomap on the actual distances, and then run isomap on the repaired distances. So in particular, I'm going to do 2-dimensional projections of the first 1,000 images of the following 5 digits from MNIST, and I'm going to knock out 70% of the data in MNIST, and still looks pretty good. Okay, it looks pretty good. I could even quantify how good a job I'm doing by trying to use this projection to classify.
Were the locations where the data was knocked out, were they random or chosen like adversarially?
I think for these experiments randomly.
So knocking out, you mean that you just remove some pixels, or you just knock out the whole image from the data set?
I knock out the pixels.
Pixels,
Yeah. Right, so it's like a 28 by 28, whatever. And then I just remove, I believe at random for these experiments. I remove at random some of the pixels, and I just make them null. And then I run, to compute distances, I run my algorithm, this funny Oracle business.
So in expectation, the distances are preserved, or what happens with later procedures?
We didn't analyze this too much more than what I told you. This is not the most rigorous part of the talk. Okay, so these are the pictures. Okay, would you like to see some pictures?
Yes.
Okay, so we got more quantitative. We are not particularly analytical here, but we got more quantitative. And we said, okay, this idea was first promoted in order to do classification better, faster, well, I don't know, faster, in a low-dimensional space of MNIST. And if you take an SVM that's trained on the low-dimensional projections with no data missing, this is sort of the benchmark, you get 94% accuracy. The goal here is not to come up with a better classifier. The goal here is to see how good a job we can do at repairing our distances and still classify fairly well. So here,
question about the idea of throwing away data. You can use the two-dimensional structure of MNIST inputs in order to replace a missing data by the average of its neighbors.
yes.
Did you try this?
I didn't try it, but lots and lots of other people have done something very similar. So note that we are not actually trying to fill in the pixel values. We are actually correcting the distances amongst these various images. So it's not that we're trying to impute the data. We're actually trying to repair the distances amongst the corrupted
Yes, but if
data.
you wanted to look at how it looks visually,
We could. There certainly in the computational biology literature, what you proposed has been done. We didn't try it here, and we didn't compare to that idea. Okay, so so here are some digits that have missing values. Can you tell what digits they are?
Zeros.
Well, I hope you can't do this easily. You can actually, if you stare at the screen from a certain direction and not from the other direction. Piotr. Huh? If you squint?
3, 5, 6, 8.
Yeah, you're right.
First one is the
Okay, it was definitely true if you look at the screen from one side.
squint, you are running by algorithm. You are averaging.
Yes. Okay. So, yes. Very good point. Yes. Okay. So I have knocked out 40%, 50, 60, 70, up to 90%, and then repaired my distances and looked at how good a job my classifier does after I've repaired the distances, and it's quite good up until about 70 to 80. Well, it definitely is terrible at 80%, but at 70%, it's still it's not bad. Squinting is a strategy.
After you repair the distance matrix, so how do you use that info to build the classifier? So you repair the matrix.
So you repair the distance matrix. Then we just run isomap. We just run isomap. You get a low dimensional embedding, and then you run the SVM. Yeah. It's all off the shelf stuff. We didn't do any of that part. Okay, so here are the the digits. Okay, so I'm going to stop here because we are exactly on time.
You can take more time.
I'm gonna conclude in words with what it is that we did. So I defined the metric repair problem, the sparse metric repair problem, and told you a number of theoretical results in the setting of what is essentially a graph algorithm, and then I gave you an application to manifold repair, an application where I don't have a whole lot of rigorous results, but they're interesting. Interesting empirical stuff. My student and I are using these ideas to look at metric learning and also to repair possibly or impute missing values to understand better the data sets that are generated by single-cell RNA sequencing measurements where you have lots and lots of zeros or unknown missing values. Okay, so that's it. That is the end of the geometry of your data sets. Okay, thank you. Are there questions, Nati?
So this, I'm not sure if that's, I think it's a bit different from these questions, but and you're throwing away a lot of information by in what you're doing here, because you could, even if you want to reconstruct the metric, you can ask for reconstructing a metric by completing the entries.
Yeah.
So,
yes.
Right. So you're by doing this transformation, you calculate these distances. You're throwing away lots of information.
Yes.
About which things should be corrected.
Yes.
So both algorithmically, I guess you can try to do actually do the completion to seek a metric instead of just increasing things. But do you have also a sense in terms of to quantify statistically how much information you're throwing away, or like information-wise?
No. It seems no. I mean
Or empirically?
Empirically, no, we don't have that either. I mean, it seems so. Given that the input to isomap is a distance matrix, it seems too much to do things further upstream. It seems like, but I don't have any way of quantifying any of that or making that statistically rigorous. But somehow it seemed like it might be the wrong thing to do because the input was actually the distance matrix, not.
You have information about what's corrupted and the corruption pattern.
Yeah.
And not using.
So no. The answer is no.
Other questions? Actually, I have a question.
Okay.
About if you think some sort of general model about random perturbations, like random erasers or something, is it then plausible that you could get some sort of convex relaxation?
Oh, I don't know. We don't have any theoretical analysis of if you have random knockouts. We do have empirical. We have a whole bunch of experiments on sort of random data sets, random input with random knockouts, and a heuristic for increase-only metric repair. I have I have to generate random points in RD, and I knock out entries at random, and I compute various LP distances. Then so I have experiments, but I don't have any. We haven't done any theoretical analysis yet. Yes.
So do you know, have you studied tree metrics?
That is an excellent question. Yes. So in particular, you might ask to. So that is a great question. So all of this work says I'm just going to correct to some metric. I don't know a whole lot about what kind of metric I correct to, and in particular, I don't have a way. I haven't told you yet about correcting to anything other than a general metric. So you can we have actually started to look at algorithms for correcting two particular kinds of metrics. So in particular, I want to correct to a hyperbolic metric, or I want to correct to a tree metric. I want to correct to an ultra metric. So that is what Rishi is doing right now. Yeah, it's a great question.
All right, let's thank the speakers.
Okay, thank you.